Hello students, in this lecture also I am going to continue with the previous topic, that is piezoelectric transducers. So I told you what is piezoelectric property and the types of piezoelectric crystals. So let's see the properties of piezoelectric crystals. What are the properties that a piezoelectric crystal must have? So these crystals must be highly stable. The first property is these crystals must be highly stable, which means these crystals must withstand higher mechanical stresses. We know that when a piezoelectric crystal is being stressed upon, or when a force is being applied on such a piezoelectric crystal, charge gets generated. So this piezoelectric must have the property of withstanding higher mechanical forces. They should be highly stable. Then it must provide high output voltage. Obviously the sensitivity of this piezoelectric crystal must be high, that is for application of forces. Higher output voltage gets higher output charges get generated, and because of that we get high output voltage. Then these crystals must form desired shape. Obviously these crystals should be in such a way that any shape can be formed from these piezoelectric crystals. Then these crystals must be insensitive to temperature and humidity. Obviously the charge so generated in the piezoelectric crystal is because of the mechanical force, and the outside environment, that is temperature or humidity, or you can say moisture, should not affect the proper working of these piezoelectric crystals. So let's take some examples. Like I've told you, quartz and Rochelle salt are the natural piezoelectric crystals. So what are the properties? Quartz is highly stable. It can withstand high mechanical stresses. That is, it is highly stable, but the disadvantage is it has very low output, means its sensitivity is low. Whereas Rochelle salt, its sensitivity is high, but it has to be protected from the moisture. It is not that it is sensitive to the moisture, and that's why it has to be protected from the moisture. So let's see the advantages of natural crystals, then synthetic materials, and the barium titanate, etc. So the advantages of natural crystals like quartz and Rochelle salt, that they are highly mechanical and thermal stability. They can withstand higher stresses. They have low leakage, and they have good frequency response. Good frequency response means, as I've told you, in a piezoelectric crystal we apply dynamic stress, means force that is varying with time. So any frequency of the dynamic force, any frequency in the sense means maximum range of the frequency of dynamic force, a piezoelectric that is to be applied to a piezoelectric crystal, the piezoelectric crystal should respond accordingly. So the piezoelectric crystals, which are natural piezoelectric crystals, they have good frequency response, means they can allow, or they can sense a larger range of the frequency of this dynamic force and respond accordingly. Then advantages of synthetic materials. Synthetic materials advantages are they have higher voltage sensitivity, whereas the advantages of barium titanate is that they can be formed into variety of shapes and sizes, and they have higher dielectric constant. Now the applications of piezoelectric, where we can apply piezoelectric crystals. Piezoelectric crystals can be applied in ultrasonic transmitter receiver. They can be applied in vibration or acceleration measurement. They can be applied in gas lighter, etc. Now let's see few derivations related to piezoelectric crystals. So we'll see how piezoelectric crystal measures force, that is measurement of force through piezoelectric transducer. This is a piezoelectric crystal, and the electrodes are placed on the both sides of this piezoelectric crystal, and the charge gets accumulated by this metal plates. So this is the thickness of the piezoelectric crystal. This is the thickness of the piezoelectric crystal, and the output voltage that gets generated is V0, and we are applying dynamic pressure or force to this piezoelectric crystal. So as we know, in a piezoelectric crystal, since it has directional sensitive property also, the charge so gets generated in the piezoelectric crystal, that is the magnitude and polarity of charge so get generated in the piezoelectric crystal is directly proportional to the magnitude and direction of the applied force. So we can say Q is directly proportional. Q is the charge generated in the piezoelectric crystal and force is the applied force. So Q is directly proportional to force. The more you apply force, the more charge gets generated. So Q is directly proportional to force. Now removing the proportionality sign, we get Q is equal to dF, where D is the proportionality constant and it is called charge sensitivity. So Q is equal to dF, D is equal to Q divided by F, and the unit of D is coulomb per Newton. Coulomb per Newton. Now I have already told you this piezoelectric crystal has is directional dependent. That is, the way you apply force, the direction and the magnitude of apply force will depend the magnitude and polarity of charge that gets generated in the piezoelectric crystal. Now, as I've told you that piezoelectric crystal works as a capacitor, and in a capacitor, if you remember, we have a formula Q is equal to C V, where Q is the charge, V naught is the voltage, and C is the capacitance of the capacitor. In piezoelectric crystal, C is the capacitance of this piezoelectric crystal, Q is the charge that gets generated, V naught is the output voltage. We can write it like V naught is equal to Q is equal to C V naught, or we can write it like V naught is equal to Q divided by C, like here we have written V naught is equal to Q divided by C. Now we also know that for capacitance, for a capacitor, C is equal to epsilon A by T, where T is the difference between the metal plates, A is the area of this plate, and epsilon is the dielectric constant, and C is the capacitance of the capacitor. For piezoelectric crystal, since it works as a capacitor, C is the capacitance of the piezoelectric capacitor, epsilon is the dielectric constant of the crystal, A is the area of the plates across this piezoelectric crystal, and T is the difference between the plates, or you can say the thickness of the piezoelectric crystal. So C is equal to epsilon A by T. Now we using this formula, V naught is equal to Q divided by C. We have already seen V naught is equal to Q divided by C. Now putting the value of C in this V naught is equal to Q divided by C formula, that is C is equal to epsilon A by T. Putting this C formula in this V naught is equal to Q divided by C, and putting the formula of Q. What is the formula of Q? Q is equal to dF. We have already seen here. So putting the formula of Q and putting the formula of C in this equation, we get V naught is equal to dFT divided by epsilon A. Now we have written these terms separately, like D divided by epsilon, then F divided by A into T. So D divided by epsilon, we have represented it by G, which is the voltage sensitivity. F divided by A is pressure, and T is the thickness of the crystal. So V naught is equal to GP. So what is V naught? V naught is the output voltage from the piezoelectric transducer. Then G is the voltage sensitivity, and the unit of voltage sensitivity is G is equal to V naught P by V naught G is equal to V naught divided by P into T. So the unit will come out to be voltmeter per Newton. So this G is voltage sensitivity, voltmeter per Newton, where G is equal to, what is G? G is equal to D by epsilon, because we have considered D by epsilon as G, where D is the charge sensitivity, as we know. Q is equal to DF, D is the charge sensitivity, and epsilon is the dielectric constant, which is equal to epsilon naught epsilon R. So this is the how piezoelectric transducer is going to measure force and give the output voltage. So this formula is very important, because this is the output voltage of piezoelectric transducer in terms of the applied input pressure. Now we will express the output voltage of piezoelectric crystal in terms of Young's modulus. So what is Young's modulus? We know Young's modulus is equal to stress divided by strain. Stress is what? Force acting per unit area. Strain is what? Change in length divided by original length, or change in thickness divided by original thickness. And force acting per unit area, stress is stress, which you can also say it is pressure. Stress and pressure both means the same thing. So this Young's modulus is equal to P divided by strain, that is del T by T. From here we will get the value of P, that is P is equal to Young's modulus into del T divided by T. Now putting this value of pressure in this formula, V naught is equal to GPT, will get V naught is equal to GPT. Putting the formula of P from this formula, P is Young's modulus into del T divided by T. So T will cancel out, and ultimately we will get V naught is equal to G into Young's modulus into del T. So this is the output voltage of piezoelectric crystal in terms of Young's modulus. Initially was the formula of output voltage of piezoelectric crystal in terms of applied input pressure. It was in terms of applied input pressure, and here the output voltage of piezoelectric crystal in terms of Young's modulus. So question may come on both the formulas. So both the formulas are important. Formulae are important. And what is del T? Del T is the change in thickness. So this is all about the derivation related to piezoelectric crystal. We'll continue with the same topic in my next lecture also. I'm ending this class here. Thank you.